Hey there. This is our third video on spring dynamics, okay? And in this video, we're going to look at the situation where we have a object on a spring, and then we have a forcing function affecting that object that has the same frequency as the natural harmonic frequency of the spring itself. So try to imagine what would happen if not only did we have the spring have its own natural frequency, but then we attach something to it, or we influence it, we shake it with a frequency that matches that frequency. What do you think would happen? All right. Well, let's go take a look at this. What we're going to do is we're going to look at, in other words, we're going to look at a situation where our differential equation looks like this. Okay, this is the situation we looked at before, and we explored the case. Case 1 we looked at was where omega was not equal to omega naught. All right, and that's what we did in the last video. Okay, so we looked at that situation, and we saw we had oscillations within oscillations. The oscillations due to the natural harmonic motion of the spring, and also due to the forcing function. But in this video, what we're going to do is we're going to look at case 2. Case 2 deals with the situation where omega is equal to omega naught. Okay, so that's the case here. All right, well, then I can just go ahead and put an omega naught there. Okay, so what happens when we solve this differential equation and these two things are the same? Well, if you go ahead and do that, all right, you're going to think of the complementary equation where we set this equal to 0, and look at the solutions that you get. All right, so take a moment, pause the video, think about the solutions that you get when you solve the complementary equation. So ordinarily we would maybe make our guess that our particular solution would be this thing. But when the complementary solution has the same value here for its omega, we have to multiply this by t to be able to find the solution. Okay? So now we're going to use the method of undetermined coefficients to find these guys. Okay? So what we'll need to do is compute yp double prime. Okay? So go ahead and do that on your own. Pause the video. We'll check our work. Okay? So 3, 2, 1. Okay, when you go through that, I'm not going to go through all the steps. I'm going to write down the final answer. This is what you should have gotten. Should have gotten this. Okay? Now what we're going to do is we're going to plug these in to the differential equation and see if we can solve for A and B. Okay, well let me just point out right now some observations. Notice that when I plug this piece here in for here, and I've got this piece over here with this chunk plugged in over here, they cancel each other off. Right? So this and this are going to die. And the same thing for this and this. Okay? The only thing that's left over is this stuff that we plug in for y double prime. All right? So what we're going to get here, what we're going to get there is this. Okay? So now we need to solve for A and B. Well, let's see. When t is equal to 0, well, this is just a 1. This term is gone. And so I see that these things have to equal each other, which means that B must equal F0 divided by 2 omega naught m. All right? Okay? And A has to equal what? Well, when I plug that in for B, I get that side exactly. I don't need anything else. So that must mean the A is 0. Okay? So I've got my particular solution. Right? My particular solution must be, and I'm going to write down the full solution here. It must be, I'm just going to use this, right? So put this stuff in place of B, 0 in place of A. So I'm going to have this thing, and I'm actually going to pull the m upstairs. So I'm going to write this as F0 divided by m divided by 2 omega naught times t times sine omega naught t. Okay? And then I need to add the complementary pieces, right? So we have cosine omega naught t plus C2 times sine omega naught t. And there we have our full general solution, okay? Now, you might say, well, this looks a lot like what we had before when we had omega naught, when omega didn't equal omega naught. But let me show you, they do look very similar. This is what we had when omega was not equal to omega naught. All right, this is what we got from the previous video. They look pretty similar, but there's a big difference here. This term right here. This one has an extra t, has a multiplied by t outside. What does that do to the graph of this? That's the question. Well, it has actually quite a big influence on the graph. And so let's look at a particular example to see what happens, okay? Okay, so here's our example. It says a 2-pound weight stretches a spring. I meant to just say is attached to a spring with spring constant, blah, blah, blah. An external force is applied to the weight, which is released from rest 2 inches below equilibrium. Find its displacement for all t. Okay? So what we need to do is we need to set up our differential equation. Okay? Now remember, our differential equation comes from my double prime plus ky equals the forcing function. Okay? Now, we got to figure out what m and k and all this stuff are. Okay? Well, what is m? M is the mass. Now, don't make the mistake of saying that 2 pounds is the mass. Remember that pounds is a force. All right? To get mass, we need to divide force by acceleration. Okay? So, the force is 2 pounds. What is the acceleration? Well, acceleration due to gravity in feet, if we use English units, it is 32. Or what do they call those? Imperial units, right? So the I shouldn't call them English because don't blame them for that anymore. They were cool enough to make the switch already, so I shouldn't be blaming it on them anymore. Okay, so the mass is 1/16. Okay, what about k? Well, k was given to us, right? K equals 4. And the F was given to us over there. So let's plug this stuff in. Okay, so we got 1/16 y double prime plus 4y equals cosine 8t. Okay, now what we did before is we multiplied through. We got rid of we made sure there's a coefficient 1 here. So let's multiply through by 16. Okay, so I get y double prime plus 64y equals this stuff. Okay, now what we're going to do is we're just going to, instead of going through all the steps that we just did before I introduced this problem, notice that it is of this form, right? So I can just use exactly what we already did. So I can kind of just jump ahead. I mean, if we did all this, we'd just be doing the same thing, right? So what did we get to as our solution? Well, we got to this. All right. Now, what is f naught over m? Well, f naught over m is exactly what's in front of the cosine function, so that's 16. All right, so let me just make note of that. F naught over m is equal to 16 here. Okay. And that's why I pulled that part up in the numerator there before. So, so what we're going to have for our solution when we go through this. Oh, wait, we have to figure out what the w naught is. All right. Well, remember what w naught is. W naught is the square root of k over m. Okay. Now, what is our k? Our k was given. It was 4. And what was m? Well, we already computed that. That was 1/16. So we have this. All right. So 4 divided by 1/16 is 64. Square root of 64 is 8. Okay. And this is the issue. Notice that the omega naught is the same as the omega. So we are in a situation where the forcing function has the same frequency as the natural frequency of the spring. Okay, and that means that, and I should have thought about that before I pointed out that this would be the solution, because it's only then that this would be the solution, as opposed to what we did in the previous video where this would have been the solution. If omega naught and omega were different, we'd use this. If omega naught and omega are the same, we use this, right? Okay, so here we go. Let's copy that down. F naught over m was 16, and we're going to divide by 2 omega naught, so divided by 16. Oh, so this stuff is just 1, all right? So I just get a t, sine of omega naught t, well, omega naught is 8, all right, plus c1 cosine 8t plus c2 sine, I wanted to write cosine again, sine 8t. Okay, good. Now let's see if we can figure out c1 and c2. Well, it was released from rest, so that tells us something. 2 inches below equilibrium, that tells us something. 2 inches below equilibrium tells us that the initial displacement is -2 inches. Now remember, we're thinking of things in terms of feet, right? So we need to convert that to feet. So 2 inches is 1/6 of a foot, all right? And y prime of 0 is, it was released from rest, so we know this is, excuse me, this is 0, okay? So if y of 0 equals -1/6, well, I'm going to plug in 0 for t, these terms go away, but this one just becomes 1, so that means that c1 equals -1/6. And what does this tell us about c2? Well, if I take the derivative, you can go ahead and do that. I don't think we need to work this out. I think we've done this enough times. This is basic calculus, right? You take the derivative, what you'll see, oh, I thought I had it written down here. Yes, c2 ends up being 0. Okay, so take the derivative, plug in 0, and you'll see that c2 is 0. So our specific solution here is this. Okay, this describes the motion of the object on the spring. Let's graph this, all right? In fact, I think I have the graph, voila, right here. Here it is. Now look what's going on here. Look at how different this is than what we saw before. Look at this. As I go out, look at this. This is just growing. It's oscillating, but it's oscillating bigger and bigger and bigger and bigger. This is called constructive interference, where we are introducing another force that is, because it's aligned with the natural frequency of the spring, it's creating this runaway scenario where the thing is just going out of control. So if this were allowed, like if the spring didn't actually hit the wall by now, it would just keep oscillating bigger and bigger and bigger and bigger. Of course, in real life, what's going to happen is that thing's going to break, right? And this is why this is so important, right? In engineering, this is a big deal. You want to make sure that the natural frequency of the thing that you're building or dealing with doesn't align with the frequencies, with external frequencies. Otherwise, this kind of stuff can get out of control and throw things out of whack, okay? So that is the situation where omega equals omega naught, all right? So we looked at 3 different situations now. We looked at the situation where there was no external force, where there was an external force and it wasn't aligned with the natural frequency, and then we looked at this situation where the external force had the same frequency. Okay. Now I just want to point out that in this example that we did, I was able to just jump to that abstract work I did and just fill in the details. Well, that's because everything lined up very well. If you've got a different forcing function on the right-hand side, you're going to have to go through those details on your own, all right, and rework all that, because you should be prepared to go through those abstract steps to deal with a more general problem. Okay, don't expect to be able to just match up the terms like I did in this specific example. All right, so that concludes this video, and I'll catch you in the next one.